bit, as I mentioned. So what I wanted to do here, I was trying to think of how I always review what I did the day before. And I thought I'd go back to this monster, this monstrosity, because it simply looks like, normally I would say that let's do an analysis of the product. I would normally want to maybe do it this way. And I would say that's K, H2. Oh, I do have a question that is like identify what's wrong with the whatever. And I think I'm going to go with a graph on that. So it's like I have a graph of something you identify what's wrong. With that said, what's wrong with this? This isn't right. What did I do wrong? Huh? What did I do wrong? Something's wrong. Huh? Yes, that's correct. For one, this is flat out wrong. This is a stoichiometric. This just shows you what you start, what you end with it. These are the real mechanistic reactions. Remember, there's a dichotomy. This may or may not be both stoichiometry and mechanism. In this case, it's not. And so this is inappropriate. You have to figure it out from here. Now, one way to know that when I'm giving you mechanisms is that, in general, I'm not saying this is when I do this. You put little K's, right? That's how you know you're really seeing the reaction mechanism. But I also made another mistake. I would say this was the mechanism. What did I do wrong? Not missing a square, but you're close.
Should we change your reactor?
No. Remember, you can express this as a change in reactants or products. I mean, the rate of change of this ought to be very close to the rate of change of that, but that's, again, there's a bit of an error.
So it's a being used reaction.
People, don't you remember? All right, we went over that. Right, so remember, rates are the time minus the time derivative of this plus the time derivative of that. But remember that as this goes away, disappears how much faster? Twice as fast, right? It's very logical. All right, so I kind of thought you were going to blow that. So anyway, that's why I gave that example. But but you're right, though, that this is actually completely incorrect because that assumes that the stoichiometric is the mechanistic, and it is not. This is the mechanism. Okay, now to nail all of this into your head, seeing how you just choked on me and all of you tried to wait and got it wrong, I thought, let's do every step. And that way, it's like so much practice, you're going to get it. Okay, now remember ultimately what the end goal is what we really want to do is due to the complication of all this, we do want to write this in terms of the rate of change of the product. Notice it's also positive. That was another difference. If it was a reactant, I'd put a minus, but it's a product. So what is this for real, given that what I wrote up there was incorrect because of the complexity of this? Okay, so, what do you think? Okay, well, here, I'll start us out K1, and remember, now I'm looking for like the rate law, right? The thing that tells me how the rate changes. So this is the rate expression, or is it? What am I missing? I'm actually missing minus sign, missing a minus sign. Usually you actually just go ahead and put it on the right-hand side, just for convenience. Okay, now what am I missing?
Concentration of BRs.
Yeah, there you go. Okay, now you got yourself a simple first order decay, right? Okay, so simple. Okay, now this guy gets a little bit...
You have DR2 spots. DR2, K2 spots. You have to include K5.
Okay, let's get to there. We'll get to there. Right. So this is actually not correct. This is not correct because, I tell you what, so I'll just go ahead and do it here. Some of you spotted this. Right, so it's being consumed, but it's also being produced. So this belongs in its rate expression. I was actually going to save that till later, but you got me. I hate you people. Now what do I do with this? Now this is a product, right? Before it was easy, it was a reactant, so of course it's going away. I brought the minus sign over here. The more of it is there, the faster it goes away. But now how do I deal with the formation?
Plus K5.
There you go, plus. Yeah, the most thing is that it's plus, right? So look, and see, the reason I like to bring this over now that it's a little bit, I can actually make this a little bit more logical. This makes it go away, this makes it appear. Right?
Oh,
Oh, no.
No?
BR squared.
There you go. Not BR2, but BR squared, there you go. Sorry, you can't see that in the back. There you go. Okay, so now you see how to play this game. Minus K2, BR, H2, right? H2 squared. But there's H2. Okay. Oh, come on, people. They're the last day together. I'm not going to show up on Friday. Okay, so, all right, so we got that. Notice I didn't write H2. Let's do this one. So minus K3, H, BR2.
Professor,
Uh-huh.
but aren't you forming DR on the third and fourth equation?
Oh, you're right. So I got to do that too. So K4. You guys actually, you managed to way jump ahead of me. I totally didn't think you were going to catch on to that, so I was planning. I actually do oddly plan. So notice that it's positive. That would be H, HBR, and okay. So where else? Oh! What do I do about that?
Why is K4 positive? Because you're still forming it, aren't you?
BR. Yes, because it's being formed. This reaction is consuming it. This is produced. This one.
Oh, okay, I see. Yeah. Sorry, I was
so
looking at the
you
wrong
say
reaction.
BR in the first term.
Yep, I see it. You missed 3.
Oh my God. Okay, hold on. All right, so I started on this one. You notice I could have latched onto either. Oh, actually, in my notes, I actually did that one. That's why. Okay, so I latched on the most complicated. So I produce it here. I produce it. Three. Yeah, this is horrible, isn't it? And then I also produce it. Yeah, I'm producing it 3, so I should have 1, 2. God, this is ridiculous. And oh, do I square it? Huh? No, you don't do anything. There you go. Okay, yeah. So this gets kind of hideous. So this guy.
K5 as well.
Okay.
You're consuming DR in step 5.
Jesus, you're right. So what was stupid about me is, and this one is squared. And yeah. So yeah, my notes I actually didn't do this one. I latched on to H. See, I could have picked either, right? They would be the same. Just for the heck of it, why don't we finish up? Let's see. This is being produced. So you can see why this is a good example, because it gives you practice. I mean, so basically plus minus, do you square it or do you not? Minus to be consumed in K4. And then I'm just going to finish this for the hell of it, just so you don't get your notes. Oh, and then see, then this is the same. I actually went ahead because you guys got me there. I had all kinds of little traps built into this. Oh, and I already did this one too. Okay, so there you go. All right, now the end. I noticed that I didn't write HBR. Why don't I just do that one? I just didn't latch onto it. But that's the one that you really want. And what you end up with is, I'm looking at the wrong page of notes, is K2 BR. Let me actually look at it. Okay, yeah, it's being produced there, K2 BR and H. Plus K3 is producing it. Those are productive. And DR2. God, sorry, my handwriting is awful today. So, and then minus, then it gets consumed in number 4. Now, what you want to do with this, by the way, Okay, so I hope this was tons of practice. Given the complexity of this monstrosity, what you want to do is really solve this guy. You could solve reactants, but let's do products, because ultimately you're making a reaction for a product. And this is kind of way too complicated to try to figure this out instead of looking at the reactants. You really want to look at the products. Now, what you would want to do with this, by the way, all right, number one thing, and I already told you this, what you want to learn how to do is represent this, not this. You want to learn to represent this on a computer and then just solve it. MATLAB can do it. I'm sure there's some online software that can solve this. It's just a couple differential equations. So once you figure out how to turn this into x's and y's and z's and all that, and f of x and f of y's and f's of z's, then you plug it into a computer. You usually have to give it, when you're solving differential equations, it actually requires a starting guess, because it might want to do it numerically. And there you go. So again, the reason that I don't really cover this extensively is that if you followed me this far with the right set of software, there's nothing you can solve. So it's like we're done. Now, but let's go back 30 years before computers and say, well, we still have to solve it. What you want to do is try to not, what you want to do, wait a minute, it bothered me, it's an H2. You want to not have intermediates, right, for obvious reasons. That's like you don't really control those, right? So when you are solving for this thing, you don't want this, you don't want this, you don't want this, and you would figure out, all right, the intermediates again are BR and H, and you would figure them out from the remainder of the mess. And then you plug those in here, and what you get is this. Actually, I know I did this example before. I actually gave you a simplification of the real expression. And I did that just because I didn't necessarily feel the need to overwhelm you, and I didn't quite think that I was going to do the full Monty. So here is the actual expression. And notice that it's not integrated yet. So this is still a rate expression. It's not an integrated rate expression. And again, you would really want to do that, or you may really have no choice, but to do that on a computer. So yeah, it's hideous. And what's also kind of funny about this one is that it suppresses, notice that it's in its own equation, which can be a bit of a problem sometimes. When it's in the denominator like this, I have no idea how you would actually solve this. So again, I just want to point out that, so you folks, you know how to do this part. My point to you is, again, you just, at that point, you're using a computer. Good for you. But when, again, 20 years ago, what you want to do is remove these intermediates, and you would come up with something like this, and then, God forbid, someone help you solve that. We're not really even done yet, and I'm actually not even sure where you go from here. Again, I'd use a computer, so I would have done that at the first step. Now, so that's really all of kinetics, but what I can do from here is show other examples. So, as much as I just said, learn to set it up and then just don't worry about it, there are a couple of like model systems, like A goes to B goes to C, that will solve them. And the point of that is that you get some intuition to how things work. Now that's useful, right? Now I don't, when I mentioned to you that when I was a grad student and I took a full-blown kinetics class, all we did is for the first month is we came up with every one of these examples we could and did the differential calculus to solve it. And that made us good mathematicians. It definitely drilled this stuff into our heads. Again, this was right before, this was about 20 years ago. Computers that could do this for us were just becoming on the market, so people were not really using them, still are not for classes, but I think that's stupid. Sorry, my handwriting is all jacked up today. So anyway, the last few examples we're going to do, again, are a couple of reaction systems which are sensible, consecutive. Let's go A goes to B at K1, goes to B, and then it goes to C at K2. you can learn you can get some chemical insight if we solve these guys. Now that I call useful. All right, now what to do with that? Okay, so you know this. You know that the change in A, we often don't put brackets around these just because it really makes my hand hurt. Here we go. And now, since there's no feedback loop, as you guys caught on really freaking fast, way faster than I thought, there's no feedback into this. I didn't make these as equilibrium, and we will do an equilibrium. That'll be the next example, or the third example. Because of that, this is just a straight up first order, just an exponential decay. K1t. Okay, so there we go. All right, now the change in B, let's do the change in B. And I'm going to forget these brackets sometimes, so look out for when I do that. And again, now that you know the name of the game, it's formed, which is positive, so that's easy to remember. It's removed by itself, so that's kind of easy to remember. And now here's the thing, you know what this is, right? So this is K1. All right, so I am showing you what the big picture is. I'm showing you how to solve the differential equations. That's the big picture here. And this is how I'm doing it. Since I have a solution for the concentration of A as a function of time, I put that in. If I have something worked out, use it for obviously the later steps. Okay, then I've got minus K2B. Okay, again, this is B. Okay, so I'm going to go ahead and do this. I'm going to bring dt over, and then we're going to integrate it. And we'll integrate it, of course, from time 0 to time t. Now remember, it's always a funky thing how you have a t in here and an upper limit of t. This really should be big T. They're not the same t, but in some ways that they are, because I'm not really telling you that this is exactly an hour or 2 hours or something like that. Clever little math trick. This will, of course, be the initial concentration of B, and that's the final concentration of B. I won't bother to write it down. And this is actually, look it up, Google it. So you can, these are examples of first order differential. This is a first order differential equation. It turns into a standard integral. Given that we just finished quantum mechanics, you know that things are not that straightforward. If this was a second order differential equation, that's the Schrodinger equation. It can be some hideous thing that, again, we might be lucky to find a 15th century textbook that solves it for us. But in this case, this is something that's Googleable, and here's what you find. Now I'm going to write all this down. It's a bit of a mess. And again, I just got it off of Google search. And I'm not really seeing necessarily what is what's the big picture. Well, I'm going to get to that in a second. So there we go. So now we have the intermediate. And what I can see in here, by the way, is, let's see, this actually represents a decay of B. So this represents B's reacting away, and this is actually its formation. Anyway, there's a rise and fall behavior to this, which is sensible. B will initially appear due to forming from A, but then it'll eventually go away as it forms C. Now, C is the end goal, right? Now, I know that at the beginning of kinetics on last Wednesday, I mentioned to you that we track the reactants. We track the reactants because that's just easy. We always set up the reactants, but when we do more complicated things, since we really want products, let's track the products instead. They really are equivalent, but let's just do it this way. Okay, now here's the trick. A naught minus, sorry, I'm having a hard time finding my notes, minus, so this is mass balance. So this is the trick. I'm sorry, again, my hand, I don't know why my handwriting's bad today. Okay, how much you started with minus all the other intermediates leads you to the only thing left, right? Yeah. So, and again, let me do a big picture. Every time I set up something, and I can set up all kinds of crazy things, right? A goes to B, B goes to C, B goes to D, D goes back to A. I mean, go nuts. And you'll find a chemical system that does that. And then you start whittling away bit by bit, and whittle you will. And every one of them can be solved differently, and every one of them has been solved because, well, I guess there's an infinite number, but all the reasonable ones have been solved, and you can find them in textbooks, or you can solve them on a computer. And so I'm just giving you a very specific one. Now, question?
Yes. Does that particular thing only work if the initial concentration of C is 0?
Well, yeah, well, I guess I would add a C0, but, yeah, I mean, I think that would be kind of a safe assumption. You're thinking of something nuclear. You're not supposed to know, right? Hey, remember how you gave me the designs from that Porsche? No, we won't talk about that. So, now here, I'm going to give the explicit answer, and there's two parts to this. One, I'm just blabbering about how to solve this stuff. But then I'm going to actually show you something that's very useful and insightful here in a minute. Just give me a minute. I know that this is just a jumble of E to the K's and T's. A question?
I'm struggling to understand why you have in the integral, why do you have the concentration of B inside the time integral? Is there a reason why you did that?
Well, I mean, this is what it is.
But if you're taking the integral of the...
Yeah, I know. It should be over here.
Oh, okay. So you just did that.
No. I did this right. It's I did this right. What you do is again, you can find examples of this. This is not an unheard of. I mean, you can find, just change B to a Y and A, that's a constant. That's your integrand. That's an X. I mean, again, this. I know you want this to be over here, but that's because you had this. That's what you saw in Calc 1. If you had Calc 7, you're dealing with this, and it's not weird if you've had enough of these classes. Right. I know that in Calc, when you're first learning integration, everything's got to be on the left, and all the other stuff has to be on the right. But as you get further along, that's not necessarily true, nor is it even feasible. But you learn to deal anyway, but you're also then a math major, right? So, and let me check my notes to make sure I'm not blabbering. No, that's correct. No, I got this right. So, again, I can, if you're curious, I found this on Wikipedia. So, okay. Again, now let me write out the whole bloody result. This is again a complex, like what the F is that? It's just a bunch of stuff. But what it leads to is something that I hear all the time and is a very interesting concept, and I didn't hear this used in professional talks. And when I hear something in professional talks, that's why I want you to know about it, because you may run into it again. Especially, kinetics. This is probably practically the most useful thing I will go over, because you can apply this to anything. I mean, yeah, I put this in context of a chemical forming another one. Well, that could be your money going to your ex. Anyway, so you get my point. There's really, how many things work like this? Everything. Everything is a kinetic process if you think about it. And so this might help you professionally. So many of you engineers, I would imagine that you might need to know this in your professional lives, but you also might. You can apply these thoughts to other things, but of course I don't know all the details of your life. So, okay. So anyway, in this very specific example, I've set up some equations, some of which we Google. Cool. Then we do some tricks. We have some tricks to solve others, and then they can be algebraized into the simplest form possible. Okay, cool. All right, but now here's a trick. Here's this trick, and you will see this a lot. Question.
Sorry, going back to what Eddie asked, the negative K2b, if you're integrating with respect to b on the left-hand side, doesn't that b term need to be on the left-hand side?
Okay, that is what he asked, by the way.
Yeah.
In Calc 1, yes, but not Calc 7. In Calc 7, you learn to deal with this. Right? This is not, again, if you had enough math, this is not weird at all. You do not know how to deal with this. You have not had enough math to deal with this. So it's like trying to understand a crazy person. Don't do it because you'll go crazy. Right? There's no understanding until you've had enough math to know how to do this. Like one way to solve these, by the way, is called a Laplace transform. Again, I've had graduate level kinetics. If you take all these differential equations, like this guy, you can actually solve this with what's called a Laplace transform in just a couple of steps. Otherwise it may not even be solvable at all. So don't freak out about this. It's just, I'm just writing down the answer because you haven't had enough math. And, yeah, I don't want to be rude or anything. It's just literally have not had enough math. I got about as far as almost a math minor just because my advisor, I came in with some AP credits, and so my advisor forced me to take more math. So I had run into some of these as a result. So tell you what, I will try to find an example of how you actually do this. I don't know if it's a Laplace transform or not, but I will find out how you do this one. I'll post it. But again, I don't want to blow your heads off with math that you haven't had yet. Not that I've done a bloody good job with that, but anyway, okay, so we're okay? Okay. All right, now here's the thing that I went through all this pain to show you something that is something you run into quite frequently. It's called the steady state approximation. So now this is the part where I'm telling you this is how you can think about this in logical ways and get good answers, and you can kind of do it in your head, and that's very useful. The steady state approximation looks at this and says, well, every time I make a B, it just goes to C. In, out, in, out, in, out. It's always just there. Maybe there's always just one B there. And if the concentration of B is basically not changing, right? Because every time you lose one, you gain one until the reaction's over. Let's not worry about that. If you're always losing one and then gaining one and gaining one and then losing one, reality is, for the most part, it's just not changing. Right? Now that's called the steady state approximation. That is when you have reaction intermediates, which you almost always do, and under certain circumstances, again, this whole, what I just said, one comes in and one goes out. If those are correct, you can do this. And what that allows you to do is, there's a big therefore. Now I am doing this from, this comes from here. If this is 0, then this is true. And then I'll show you what you can do with this. Sorry, I'm just K2B. Okay. So this is what that allows you to do. Now notice what I can do now is I can say that therefore the concentration, sorry I'm not using the board too well, concentration of B is just K1 over K2, right, concentration of A. I've already worked out the concentration of A, so this ends up being K1 over K2. Initial concentration, E to the minus K1T. Okay. All right, now what does that allow you to do? Sorry for my horrific use of the board. And again, I see this all the time in talks. I see people say, oh, and then we do the steady state approximation, and or sometimes they explain things in a steady state. I don't know why anyone would use the steady state approximation to solve things anymore, because like I just was rambling on about computers and whatnot, and there's just unbelievably simple ways to do this. Okay, so all right, we know this from up there. I didn't write it down, but anyway, and so this has to be K1A. Again, that's from the steady state approximation, and therefore, when you integrate it, you get this, and this is a very simple integral. You get, I'm not going to go through it. This is one you've done, but I've kind of run out of time here. There you go. So you end up with a very simple expression. again, this would be a, if you graph this, it would look like this, by the way. Again, I used to do this all the time, so it looks like that. 1 minus e to the minus kt. Like I say, this is what I did in grad school. Okay. Now, again, what is very useful is that you can kind of do this in your head if you do steady state approximation. I hear this all the time. I hear things sometimes solved. Again, I don't know if I get that. I hear things explained with steady state. That's what they're talking about. Intermediate concentrations are not changing. But now, what's more important is this is an approximation. It may or may not be valid. Now, to do that, now this again is kind of like a bigger picture thing. Let's look back at wherever the heck I wrote that monstrosity. Okay, so this is the exact expression. And I'm going to write that again. That horrible mess on top. And what this allows you to do is figure out when is it valid to do a steady state. And again, that's very useful. And, okay, so I'm just writing this, blah, blah, blah. Okay, so I see I've got a naught on both sides. I'll tell you what, let me bring this over here. I'm not changing it, I just want the a naughts to be on the same side. Okay, so what I see is I have to figure out why. Now remember, this is exact. I wanted to go through the bloody mess so that you could see this and then try to understand how does it turn into that. Right? Now how does that turn into that? You're going to have to make some assumptions. Now, for one, there's nothing in the denominator here. Sorry, they were not close together. The world will explode. There we go. 1 plus something. I got 1 minus something. So that's a bit of an issue. This has something on the denominator, and this doesn't. Okay, so that's a big clue that I'm going to need to get rid of. Okay, there's a couple of things, right? I can't have a denominator, and I can't have a K2, right? So how do I do that? So let me give you a hint. All of this is gonna have to do with relative rates. Now, what do you think? What do you think? One of these needs to be way bigger than the other. I think I know which one it is. One of these needs to be way bigger than the other. Which one is it? All right, I had to vote for K2. Any K1s?
I'm saying K1.
You're saying K1 to be difficult. You've been here for a long time. I know that is right, aren't I? Okay, if K1, okay, the problem with K1 is that, let's see, I would end up with a K1 on bottom, a minus K1 on bottom, right? Because it just basically overwhelms that. And then this term would survive, and I'd have a K2 in the final expression. So it's the opposite. There you go. So it's K2 is much greater than K1. Okay. Now let me walk you through that. Okay. So on the bottom is now just K2, right? So now what's going to happen is, well, you see the reason is that this gets wiped out, right? E to the minus big number is what?
0.
Right. Right. It's wiped out. So you end up with K2 minus K2, K2 e to the minus K1t, A naught, and oh God, this is sorry, but I don't know why my handwriting is so bad today. And I'll answer your question in the back. Just 1 second. Okay, so, and notice that the next step is that it turns into that. You see that? Because the K2s are canceled. See that? Does that actually answer your question?
What was your reasoning for saying K2 was significantly larger than K1?
Because I'm trying to figure out why this would turn into that. Right now, remember, this is a steady state approximation. This is the exact answer. So under what circumstance is this that?
Okay.
Now, the reason for that is then this tells me why I can use the steady state approximation. And the answer is when K2 is greater than K1, like a lot bigger. Okay, now let's go back and look at this thing. What does it say about the actual reaction? Remember, I was telling you that the point of this is to look at the reaction and understand it a bit. You see what happens? K2 is greater than K1. So what happens is, whenever B forms, it takes a while. Every couple minutes, one shows up. When it shows up, what happens? It's immediately gone. Right, so that's when you have the steady state approximation. When the intermediates show up, but they're gone in the gunshot. So they're basically never there. But that's valid. Not being there, never being there, means your concentration's constant. It's just zero. But that's still constant. So that's the circumstances under which it works. And again, you get a nice, just simple rise, like a little exponential rise in your product there. Let's see, one or two others you asked. How about I'll do just one more, and that's really all I have time for anyway. One of you asked about equilibrium, and I thought I was actually very glad that got answered, and I was always planning on looking like this out. I was planning on doing it today because what I said, one person said, no, wait a minute, what happens when you have an equilibrium? And I said, equilibriums don't exist if you choose to analyze it via kinetics. So you can analyze equilibrium with equilibrium constants, there's nothing wrong with that, assuming you've reached equilibrium. If you have not reached equilibrium, you can analyze things with rate constants. Now, rates, if you get rate expressions, insert time infinity, and now you have equilibrium constants. So rate expressions are actually more useful than equilibrium constants, because rate expressions tell you how you get to equilibrium and what it looks like when you're at equilibrium once time has gone to infinity. So now that'll be more clear. Again, I don't have much time, so let me just power through this. And again, I will try to look up that integral. You guys were more perturbed by that than I thought, but that's fine. You're curious. I'm glad about that. A question?
Are we going to have to solve that integral in the final exam?
No. It's the extra credit. No, I have an eigenvalue equation. The extra credit's an eigenvalue equation. It's hideous, by the way. So don't do that. Do that one last. I'll tell you all on Friday. You're not going to tell you everything on Friday. Okay. Sorry. Let's just do this guy. Now again, you can think of this the equilibrium constant as concentration of B over concentration of A, right? Now you know that. Let me show you how you can learn more about the underlying what the heck is going on via rate expressions, right? Now we've learned how to do the setup game, and I haven't. Now that we've actually had this discussion, now again, I can't emphasize enough. Like when I took this in graduate school. What am I doing right now? I'm using that mass balance thing, the fact that the concentration of B has to be the initial concentration of A minus the one going on in time. I'm doing this because I know that it gives me the answer very quickly. I don't know how the first person thought to solve it this way, but if they did, they got to it quickly, and when they realized that this is the best way, that's what they put in textbooks, that's what I've read, and that's what I'm showing you. Question?
Yes. Can we, instead of calling it K2, call it K minus 1?
Because I'm calling it K minus 1.
Or vice versa.
No, traditionally done as minus 1. Sorry, it's I don't know if it's my notes or I'm just speaking too quickly. Okay, so now again, guys, don't bite my head off, but this is a standard. This is Googleable. It's basically the same thing we ran into a minute ago. And let me show you this. Now again, it is actually surprisingly kind of painful to see this, and I want to also remind you that computers can solve this. Not only can computers solve this via e to the t and yada 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 like I'm doing right now, but computers can also just say, oh, just tell me what was the initial condition. Oh, it was 1 molar of starting material, and then it can just numerically punch out numbers, and that's what you get. Okay, now, awesome. But now we wanted to talk about equilibrium. So at t goes to infinity, what happens? Huh?
Zero.
Right, 0. Now let's call it equilibrium. And this is K minus 1, initial concentration of A, K1 plus K minus 1, and concentration of B at equilibrium. We do the same trick. It's A naught minus this, right, would be the concentration of B by mass balance. And again, I don't know how, I always ask myself if I was living 200 years ago, that's about what this was probably worked out. Would I have figured it out? And I don't know. That's hard to know those things, right? So there you go. So that's the end, and no, I'm just kidding. So the only magical thing is how I went from here to here. And again, I'll try to find the mathematical examples of how that gets done. And hopefully it's tractable. But now you know that the equilibrium constant is products over reactants. We don't have anything squared or anything weird or to the half in this simple example. And what is it? K1 over K minus 1. Ta-da! Does that make sense? Right. You got more B if K1 is dominant over K minus 1, and vice versa. And that's also the equilibrium constant. So you can put equilibrium constants in terms of kinetic rates. They have to be the same thing. You just don't see T in the expression because you allow T to go to infinity. And again, that's just another use of kinetics. Okay, oddly, it's on time. So again, remember,